So I've made a kind of a wacky little setup here in my living room. It's an old curtain rod and there's a ball mounted on a spike here. The idea to be hoping to give you a, the duct tape is failing. Hoping to give you a sense of the kind of problem we want to consider, which is you've got a line in 3D space and a point somewhere off, but not on that line. How far apart are they? And I think people get, right away, they get a reasonable idea about how you should measure this. If you had a tape measure, you'd go, well, they're about, looks like 12 inches. But, you know, that's, what I intuitively jumped to was kind of measuring the distance straight from the ball to the line. Why didn't I want to measure like there or here? Out of all these different lengths, which one is it that is actually the sort of correct distance from the point to the line? And what it really is the least value you would get. As you move a point along this line, there comes a point where the distance comes to a minimum. Actually, I think it's more like 13 inches, but whatever. And then it gets bigger again as we go farther away. So when does that minimum distance occur? It occurs when this line connecting the point to a sort of moving point that's going along the line, when that guy is perpendicular to the direction that the line is going. So that's the kind of, that's the first question we're going to try to answer in this section. Then we're going to take it one more step, and instead of a line, we'll have a plane, and we want to figure out distance between a point and a plane. But let's start with the line. The main trick is to then come up with a good way to write the equation of a line and then come up with the distance formula, that perpendicular measure of distance between the line and the point. No doubt you've heard the saying that 2 points determine a line. So imagine these are points in three-dimensional space, P and Q. Of course, they are 3 points in 3D space, but they're stuck on my flat blackboard or whiteboard. Nevertheless, you can imagine a line going through them. Try to get it to go through both of them. And let's call the line L, or line. So the coordinate frame might be down way over here, right? Here's the X, Y, Z system that determine, you know, you would write these guys' positions in terms of. Well, I want to give you the vector version of thinking about this equation, because that's really the most succinct, and it's kind of the point of having vectors. To get to a point on the line, what you want to do is take the vector that goes from the origin out to P, so that's vector OP, and add to it some multiple of the vector that goes from P to Q. So if I added 0 times PQ, I would just have this position vector. If I added 1 times PQ, I'd be out here. If I added 2 times PQ, I'd probably be just off screen. Minus 1 times PQ added to OP was back here. So you can think of this multiplier I'm giving you on PQ as time. That is, you say your eventual position is the vector OP plus some multiple, and I'm going to call it T, times PQ. In fact, if you'll indulge me here, we should think of this as a vector function. That is, it's x as a function of time. That's equal to OP plus T times PQ. There's a bunch of ways you can write the equation of a line in 3 space. The one I've given in general can be said if you've got a position vector and a direction for the line. That's what PQ really specifies for us. In fact, it does a little more than just saying the direction, because think about this. If this is where you are when t is 0, and this is where you are when t is 1, doesn't the length of this thing tell us how fast we're going? And its direction tells us which direction we're going. And if you go this distance in 1 second, you're using that distance per second is your speed. The direction of it plus its length, that magnitude, that vector, that's your velocity. So let's collect up some of these different ways of referring to the equation of a line. Kind of taking the points out of the issue, you can say the function x of t that gives you a moving point along that line is some initial position vector plus t times some velocity vector. Let's put some coordinates on those things. So suppose we had the position vector. Well, this is a fairly common way to talk about where you are when t is equal to 0. Have little subscript zeros on the position vector's components. X naught, Y naught, and Z naught are where you were located when time is 0, because that's what, well, if t was 0, this part wouldn't be there, and so you'd just get your p. The velocity vector's components, I'm going to stick with what they do in the book and just call them ABC, because, writing them as, well, writing them in other forms might be strange. Anyway, these are the x, y, and z components of our velocity vector. So you can write out the complete thing as a vector equation. That x is, well, let's just call it x, y, z, is equal to our position, which was the variables with subscripts on them, plus t times your velocity. So that's sort of an expanded form of the much more compacted notation up here. I noticed, you may have noticed that I just used x, y, and z in here. If you like, you can emphasize that these coordinate locations depend on time as well. This makes it a vector that has components that depend on time in it. I'm just saying that we can leave that time dependence as sort of implicit. We don't need to necessarily specify it this way. So I'm going to get rid of that because I want space for something else, which is you can use the vector operations on a thing like this. You have a time as a scalar on the outside, and you can multiply it in, kind of distribute it across those components. And these two things are then two separate vectors. Well, why not add them up? So this is equivalent to writing x naught plus t times a. Let's see, the middle would be y naught plus t times b. And in the z coordinate, it's a z naught plus t times c. So if you didn't have vector notation, what you would do is just say, well, what we've really got here are three scalar equations kind of combined into one. That is, x is equal to that, y is equal to that, and z is equal to that. That's scalar parametric form for the equation of the line. Why I call this parametric, because all of these are parametric, is that there's a parameter. That's what t is. T is a variable that you imagine changing, and it smoothly changes your position along the line as you change it. So yeah, the scalar parametric form just looks like plucking out what's happening in the various coordinates of the vector form there. X is x naught plus TA. Y is y naught plus TB. And finally, Z is Z naught plus TC. That's not very profound. And I hope you see that the vector form has actually got the same content in it. And when you don't expand out in terms of coordinates, it's really quite compact. Compare what's at the top of the board to what's at the bottom of the board. So that's one of the reasons we like vector notions. Okay, so that gets us the equation for a moving point on a line. So effectively it gets us the whole line. If you think about as t changes, the point in motion sweeps out the line. There's another variant of the equation of a line not given in the book, which I think is unfortunate. So I'm gonna add this to your knowledge base a little bit. It's called a convex combination, or forming a convex combination. Oops. Okay. So let me show you what this is for. If you have, let's put x, y, and z down here, and a couple of points here and here. So think of that as P and Q. There's a funny spelling error in there. Combination. I don't know, maybe there's like a vertical dyslexia there. That's supposed to be a B. Combination. Anyway, you've got vectors that go from the origin, O, to P, and separately to Q. So we've got OP and OQ. Those are easy enough. What I mean by a convex combination is to do something so that when t is 0, you're here, and when t is 1, you're there. So as t ranges from 0 to 1, you get this segment that, let me put it in red. We want to get an equation for this segment that depends on the parameter running between 0 and 1. And why are 0 and 1 so nice? Well, you can make it happen that when time is 0, you'll be here. And you can make it happen that when time is 1, you'll be here. And you can do it really, I think it's a clever idea. You just, you think about these two vectors, OP and OQ, and you want to add them in such a way that one of them gets t and the other gets 1 minus t as its multiplier. So I'm going to put t on the second one and 1 minus t on the first one. And that trick is what works over and over again when people are talking about making convex combinations. A parameter and 1 minus that parameter. So think about it. When t is 0, what's this? It's 1. Where are we then when t is 0? We're at p. Because we have 1 times OP and 0 times the other thing. What about when we let t run up until it gets to 1? Well, 1 minus 1 would be 0 times the OP, and 1 times OQ would get us OQ. So it's easy to check that you're going to be at P when time is 0, and you're going to be at Q when time is 1. But if you think about what this ends up being, it is a linear item. If you worked out the coordinates of it, they would all just have, well, the same shape that we had for our parametric forms of the equation of a line. The x, y, and z coordinates of everything will look like a constant plus another constant times t. Perhaps it would be a good idea to put some actual coordinates on things, and then you'll see how that works out. So let's suppose this p here is 1, 1, 3. I would say is about what it looks like. And q, that's a lot farther out in the x direction, only a little bit higher, and maybe it's a little bit farther back. So about, is that 5 in the x direction, 2 in the y direction, and I'm going to say 4 in the z direction. I wanted it to be roughly to scale. Right? So what I've done here with our t times 1 minus t times OP plus t times OQ, that can now be translated into a vector equation with numbers in it. 0 to p is literally just write that as a vector. So our position vector is going to be equal to 1 minus t times the vector 1, 1, 3. And then the other piece is going to be t times the vector 5, 2, 4. Well, like before, just because there's variables in it, don't let that scare you. You can still do scalar multiplication, which just means distribute the variable into the parts of that. So we get, we do it as in 2 stages, 1 minus t, 1 minus t, and 3 times 1 minus t. That's what's in our first vector. Our second vector, I don't have much room for it, but it's okay because it's smaller. It'll be 5t plus 2t plus 4t. I think I just said plus, didn't I? I shouldn't have said plus. It's 5t comma 2t comma 4t. Okay, now let's add those things together. The x coordinates are 1 minus t plus 5t. That's 1 plus 4t. The y coordinate, it's 1, and then a minus t, and then a plus 2t. So it's 1 plus t. And then the z coordinate, wow, it's 3 minus 3t plus 4t. That ends up being 3 plus t. So that's what you get from thinking about convex combinations. It's really the same. In fact, I sort of was thinking you want to stick 0, less than or equal to t, less than or equal to 1, put that constraint on it. But you could remove that constraint, and then this equation would just continue to work for the whole infinite line. T negatives would be back this way. T bigger than 1s would be out that way. And beyond that, you can see it as looking like a position vector plus a velocity vector times t. Let's just do that last thing, and then we'll move on. So let me re-express what we've got there at the bottom of the screen as a position vector plus t times a velocity vector. It's 1, 1, 3 is the position part, and t times, the things that t is multiplied by, 4, 1, 1. So that I'm saying would be your p, and this would be your v. You can read it out of the form of the equation. All right, so the whole point of this was for us to figure out what's the distance between a point and a line. This is an important starting point, knowing what the equation of the line looks like. But let's get on to doing that distance calculation now. Right, so we're going to need a line, let's call that L, and a point that's on the line, let's call that one P. Really, I'm thinking P, but there's also the vector P that is a position vector for on there. So you might think about a vector coming from the origin out to there named vector P. The other component you need for the equation of a line is the velocity vector, which is, let's call it V. And there's the tip of it right there, lying along the line. All right. Now I want to have a point Q that's kind of somewhere off in space away from the line. There it is. So what I want to do is figure out the length of this line that I'm putting in dashed line, in dashes. That's perpendicular to L. Well, okay, there's one thing I can do for you, which is make a triangle. It's floating somewhere weirdly in space, but it's a right triangle. Do you see it here? This goes, the hypotenuse is from P to Q. This unknown length we're after, the distance, which, yeah, we don't know what it is yet, is there. And I don't know what this is either, but I do know it's in the direction of V. It's kind of intriguing. Can you work out what that right triangle's parts are? Well, I mean, beyond that. Well, there's an angle right here across from the side we're interested in. And notice what that would be. That would be the angle between the velocity vector and PQ. So theta is the angle. Oh, I just said it. Let me just write it down. It's the angle between PQ and the velocity vector. So if we do a dot product computation with V and PQ, we'll get the cosine of that angle out. Problem is, I don't care about the cosine of this angle. What I want is this side that's opposite theta. What trig function is that? Well, if I knew the length of PQ, the hypotenuse of this right triangle, and I'm after the opposite side, I need the sine of the angle. Remember how the cross product actually the formula looked the same as the dot product, except it had sine theta in it, and some absolute values? All right, so think about this. How big is, excuse me, not you. How big is the vector PQ crossed with V? What's the size of that cross product? Yes, it is equal to the product of their sizes times the sine of the angle between them. That is the product of the length of PQ and of V and the sine of theta. And the distance I want, this distance, I can tell you what it is. It's sine of theta times the length of PQ, isn't it? PQ's length is the hypotenuse of the right triangle, and so I think maybe you might see it the other way more easily. D divided by this length would give you the sine theta. Right? So the cross product has basically got the junk we want in it. It's got the sine of theta, it's got the length of PQ. We just need to not have that V in there, so you can make that happen easily enough. Just divide both sides by the length of vector V, which will just cross that one out, right? And what is this after all? That's our distance. That's a pretty cool thing that you can just take a cross product, divide by the length of the velocity vector, and by the way, think about this in terms of the velocity vector. Why should the velocity have anything to do with this distance? It shouldn't matter whether we go down this line really fast or really slow. The distance is still, that perpendicular thing. So we oughtn't really depend on V's size. Of course, the cross product does, but when we divide out by V size, it no longer does. Okay, so D, yay. I think that's kind of cool that you can just throw a cross product at it and get the distance. Well, we want to repeat what we just did, but for planes. So here's a crappy model of a plane. You've got a plane sitting in space, and you've got a point that's not on the plane. I guess I need to rotate this so you can see in here. I want to be able to figure out how to measure a distance from this point to the plane. It looks like about 10 inches right now, just using my tape measure. And notice which way I'm measuring. I don't measure out this way, I don't measure out to there, I measure square to it. I want to have this dimension be measured in the direction perpendicular to the plane. So let's get on with doing that. It's going to follow a similar pattern to what we did a second ago. We're going to first figure out the equation of a plane, and then use it. And the thing that will take the role of the velocity vector in that is the normal vector for the plane. Okay, so, should have erased. I'm just drawing a parallelogram in space, but it's really supposed to be a square that's kind of showing you a plane. It's at least just this is to a plane like a line segment is to a line. You should imagine it extending off in all directions from there. There's going to be a vector normal to this plane. We almost always call n. That is, it's 90 degrees from it, in however you measure. And the vector, the point there in the plane, again, x, y, z's origin will be like down here. Here's a vector to a particular point in the plane. We'll call it, well, it's a position vector, so why not call it p? All right, so we actually kind of did this in a activity. If I think about an arbitrary position vector, well, let's just call it x, vector x, but you know, x, y, z coordinates. Is that guy in the plane? Well, it doesn't look like it. And how could I tell that it doesn't look like it? Well, it's literally not on it, right? I mean, we'd have to be up in here, but look at the vector that goes from the tip of P over to x. Does that seem to be normal to this vector n? No, there's an angle in between those. I don't know. It's not much, but there's a slight angle. So if I wanted x to lie in the plane, I have to move it. I have to kind of, let's just take it out of there and put it on the plane now. Now the vector that goes from P to x, because the label for x needed to move too, now that guy is in the plane and it lies perpendicular to n. So what's an expression for this vector that goes from the tip of P to x? Well, P plus that thing is equal to x. So x minus that thing is equal to P. That is, this vector I've been talking about is x minus P. Have I said that right? What happens if I add P and x minus P? Just check that. Yeah, you'll get the P's will cancel, you'll get x. Cool. So x minus P is this vector that goes, its initial point is at the tip of P, its terminal point is at this arbitrary x. But the condition we want is that that sucker is perpendicular to this n. Okay, so here's the equation for our plane. N dotted with x minus P, everybody's a vector, should be 0. That's one way to think of the equation for a plane. Let me, before we push on, let me illustrate another one and then show you how they're connected to each other. Another way of thinking about this, again, here's an XYZ system down in the corner, and we'll have a particular point, and I guess I want to draw the plane as well, or at least a piece of it. So we've got a vector P that comes out to that, and oh yeah, there's the normal vector, just like there was before. But what I want to do is think of this plane as a collection of the tips of vectors. So there's a whole bunch of vectors that we want to think about whose tips lie in that plane. What do those guys all have in common? They all have the same dot product with n. So if you look at any one of those, think of it as an x. N dotted with any of them gives you the same result. And I'm going to call it k for constant. They all have the same projection onto the direction of n, which is kind of cool because that's really the idea, right? They project all the tips of these things. If you squeezed them in until they had it on n, they would land on n's initial point. Watch out that that's a scalar, not a vector. So those two are vectors, that's just some number. And let's see the connection between these two views of things. If you dot n with this difference, let me just pop it up here, you'll get n dot x minus n dot p is equal to 0, the number 0. So that means, wait a minute, that means that n dot x is equal to n dot p. If the difference is 0, that means the two things are equal. So for nx equals np. Well, compare the left sides of this, nx, k, np. It must be that this np here is indeed the same as whatever the constant is. And that makes perfect sense if you think about this is one of the vectors, p here, that goes to that special point we chose in the center of the plane. Yeah, if they all have the same dot product, then in particular p has the same dot product. That's what k is. N dot p is equal to this constant parameter. So these are identical in a certain sense, but they're different in a slight philosophical sense. This has you thinking about the plane centered at P. Here, P doesn't really have any particular importance. P is just one of many. Here, P is the point that tells you where the middle of the plane is. All right, so now that we're there, let's try to figure out how we can calculate the distance from a point to a plane. All right, so we're going to think about a plane and a point not on the plane. For simplicity's sake, I've drawn the plane as if it was horizontal. So this would be like the x direction and not the y direction. I know it's in perspective, but imagine it's horizontal. I'm only doing that for simplicity of the drawing, not because we need that. So if you like, you can turn your head to some funny angle and look at the plane as if it's not horizontal. This is one of the advantages of doing things in a coordinate-free fashion. Let me put that another way. I haven't shown you where the XYZ system is, have I? Well, maybe it's here with Z going that way, X going this way, and Y going that way. It's in some strange orientation. Now that plane is not really horizontal, so just for the purposes of my picture, I've laid it horizontal. All right, we will drop a line to this plane in a perpendicular fashion. That line is going to hit the plane at right angles. In fact, you see that line goes in the direction of n. You know what else I'm going to need? I'm going to need a point that's on the plane somewhere. So we've got a point off the plane, call it Q, and a point that's in the plane, called P. And those guys, those guys determine a line, right? A line segment. The length of this would be the length of the vector from P to Q, I suppose. Do you see a right triangle emerging? It's kind of nice. There it is. Now, all right, what are the sides of that right triangle? Well, the hypotenuse of it is this length that goes from P to Q. So the hypotenuse, I guess we should call it H, is the length of vector PQ. And the side we're interested in, the distance between Q and this plane, is the side opposite something. Or is it the side adjacent? Wait a minute. You got to think about where is the angles that are known on here. If I had vector PQ, I might as well draw it as a vector, and I have vector n, those two things, they have an angle between them, right? And it looks like that I might have to translate this over here and see what the angle was there. But you can spot that angle in another place because, like I said, this distance here, that's measured in the same direction as n. So this could be a copy of n right here, or except for its length. Might be different. In terms of angles, though, there's our angle. Theta is up there near the point Q. All right, so what's this unknown side that we're after? It's adjacent to the angle. So this distance is the cosine of theta times the hypotenuse. we've seen that before, haven't we? That's almost all the stuff that goes into figuring out the dot product of n and p to q. Remember that n dotted with pq would be, well, it has the length of n and the length of pq, and additionally the cosine of theta. We just have everything there except for the length of n. So as before with the velocity, how the velocity vector really shouldn't have had any impact on our calculation of distance to a line, well, the normal vector really shouldn't have any impact on the distance to the plane. I mean, if I made n 3 times as long, went way up there, does that change how far this is? It doesn't change the plane, it doesn't change what set of points the plane is, and it certainly doesn't change this distance. In fact, I could make n negative and have it go this way. It still wouldn't affect this. So n shouldn't be a part of the computation. So d is take this dot product and divide out by the length n. That's pretty fun. Except it's slightly a lie. Slightly a lie. What the problem is this. The dot product we got here between these vectors, I've drawn it as if n and pq are pointing roughly in the same direction, so you were thinking about the dot product comes out positive. But that was just a drawing, right? You have to be aware that drawings sometimes fool us. What if n went this way and pq went that way? Now their dot product would be negative. Well, we can fix that. Put a plus or minus in here, or put absolute values around the whole thing if you like. Or just around the dot product part on top. So just watch out for that issue. If you get a distance that's negative in a computation, it just means it's not the direction you thought. You thought it was above the plane, actually it's below the plane. Okay, another little piece that comes from the equation of a plane is when we have, certain planes bear geometric relationships to one another. They can be parallel to one another, or of course they can be orthogonal. And we wanted to see what conditions on the equations let us know about that. So I've drawn, roughly speaking, a pair of planes that seem to be parallel to one another. And let's assume that they are. What would you get out of that? Well, they each have their own normal vector. The normal vector for one plane might be like that. The normal vector for the other might be much longer. So maybe I should call them n1 and n2. Both of these are normal vectors though, so they're perpendicular to their planes. If you want the planes to be parallel, what has to be true about these guys? They have to be parallel as vectors, which means that the vectors have to be multiples of one another. So normal 1 is equal to some constant times normal 2. Now that happens to make the constant look like it's a positive big number, but of course it could be the other way around. In fact, the normals could be in opposite directions, so k could be a negative number too. All right, so that's easy. Parallel planes have normal vectors that one is just a multiple of the other. Should I write that out? I guess so. Parallel planes have normal vectors that are scalar multiples. By the way, that's a shorthand. You don't have to say normal vector. You can just say normals. I suppose I could also get away with not saying scalar and just say that are multiples, but I've already written the word now, so I'll stick with it. Scalar multiples. I kind of want to say of one another too, because I'm wordy, but it's a complete sentence as it stands, so I should stop. What about perpendicularity? Whether you want to say the two planes are orthogonal. There's something funny there because planes can be orthogonal in lots of different ways. Here's two planes, right? My pack of my cardboard thing and the notes I've been working off of. They're perpendicular like that, but they're also perpendicular like this or like this. I can have lots of different plane, given a single plane, I can have lots of other planes that are perpendicular to it, orthogonal to it. So how do we distinguish? Well, it's not so bad because the distinguishing property is that a dot product comes out 0. If I have a plane that is perpendicular to this first one, I have it sticking up through the middle of it like that. But it's also down here too. Oh, this part should be dashed now, shouldn't it? Since that back edge of the plane is behind the other plane. How are this guy's normal vector and that guy's normal vector related? This guy's normal vector is kind of pointing out towards us. So this is the new N2. Well, it's not that anymore. In fact, what you want is the normal vectors to be perpendicular to each other. Well, I just realized I have a labor-saving possibility here. Perpendicular planes almost erased it, and then I wouldn't have to have normals that are, yeah, scalar multiples won't be the case anymore. That would be parallel. But so maybe I didn't save that much writing. Perpendicular planes have normals that are perpendicular. Let's just say because I'm trying to save writing. That means that N1 and N2 are going to be orthogonal vectors. That is, they have dot product 0. Well, that's pretty cool. There's another piece of this puzzle that gets left out of the textbook, which I would kind of like to have us see. So bear with me for giving you a bonus section here. Sometimes you want to have, you may have noticed for the plane, we did not have a parameter. It was just the plane was described entirely in terms of its normal vector and any vector that lies in it. With a line, on the other hand, we had a parameter. Is there a parameter version of this stuff for a plane? And yes, there is. So let's imagine we have a plane, and here's a point that's in the plane. I'll put my XYZ system down in here. So that is position vector P for, and you want to think of P as now defining the center of the plane. But, really, I guess the way we should start this is with geometry. It takes 3 points to determine a plane. Once you have 3 positions in space, you can balance a plane on them. Of course, not if it's the wrong way. But you know what I'm saying? It's like a tripod. In fact, that's why tripods work so nicely, because 3 points determine a plane. So I need some more points on here. How about here's another one and here's the third one. Those 3 points would probably originally be the things that you would use to define the plane. Let's call them P, Q, and R. All right. So I'm picking P as being the center of the plane, and so the position vector that corresponds to the point P is the vector of a point that is at the origin, really. That's the center of this plane. But what I'm going to do for the axes is it's going to depend on Q and R. So I'm going to make the x-axis, just because, I don't know, this orientation seems right to me, run through P and go through R. So think of that as your x-axis. But let me put quotes around this x, because it's not really, like the x-axis is down here. But it's sort of x for the plane. And similarly, you've got a line through P to Q, and that could be your, quote, y-axis. All right, so those points, PQ and, sorry, I should just say Q and R, they have coordinates that we know. This length from P to Q is sort of the yardstick for measuring things in the y direction. And that's the point 1 unit out, because by definition, its length is the unit from the origin in the y direction. That's 0, 1. 4 coordinates in this plane. And this guy here, r, again, its length is the thing we use for measuring lengths in the x direction. So that, by definition, is 1 unit out. And so that's 1, 0. Their sum would be there, and that would be 1, 1. And you can imagine taking multiples of p and multiples of pq and multiples of pr and getting to all kinds of different points in the plane. In fact, that's what the parametric form for the equation of a plane is. X, a position vector, is going to be a function of 2 parameters. Let's call them s and t. And it looks like this. You have your initial position, p, plus, let's see, s times the vector from p to r. So s is like your x coordinate, and t times the vector from p to q. So that t is like your y coordinate. The flaw with this, though, is that ordinarily the system you get by arbitrarily choosing points and laying, and doing this, well, it gives you a nice parametric form for the equation of the plane. The coordinates are usually terrible. Let me take away the 3D-ness of this. Imagine rotating that plane into view in front of us and see about how this coordinate system looks when we're staring it straight on. The problem is that the coordinate, once you've laid the plane out flat, here's its origin, here's its x-axis, and here's its y-axis. Actually, let me exaggerate the difference. Suppose the x-axis is really short and the y-axis, or the vector in the direction of the y-axis is really long. Then you get this kind of bad coordinate system that has differences between the two axes. We measure x directions differently than we measure y. Plus, aren't we kind of used to having x and y axis perpendicular to each other? This wouldn't be like that. You'd have this rhomboidal collection of unit squares. I guess you should call them unit squares still. But, the coordinates on this would be a little ugly. One of the issues is that changing your x position, your position in the direction, these were the points P, Q, and R, right? Moving a little bit in the PR direction actually also changes where you are in the PQ direction. So we really prefer to have axes that are orthogonal. And we really prefer to have axes that are the same length. Now, it's actually not so hard to do, but maybe a little beyond the scope of what we want to do today. But you could just rotate Q over and then shrink it down. It's a process called, the Gram-Schmidt process. You can orthogonalize the coordinate system there. But that's for a later date, actually for a later course. You might take linear algebra and you'll see that. Okay, so that's it for stuff at the Blackboard today. We're going to go over to my screencasting setup, and I'll show you a little trick on Sage, because I think some people were having trouble with cross products. So I want to make sure you all have a computational way to deal with that. I just wanted to do a brief bit on how you can use Sage to verify your work when you're doing cross products, because honestly, cross products can be difficult. And, it's easy to make a little error and end up with a sign error, for instance, and get one of the coordinates of your vector is the negative of what it's supposed to be, that kind of thing. So it's nice to have a way to use a computer to verify what you're doing. So first, how do you construct a vector in Sage? Probably not much of a surprise. There's a function called vector. I tab completed it. I just typed VECT and then hit tab, and it's gave me the vector constructor. Now, if you want, you could pull up the help on that and see sort of the different styles of ways you can call the vector constructor. But honestly, there's a lot of detail in there about higher level math that you don't really need to know. Not for now, anyway. So here's a sort of straightforward way to construct a vector. First, you tell it what kinds of numbers are going to be in the vector. And writing double Q like that is kind of shorthand for the rational numbers. So we're going to have a vector with rational entries. I'm going to make a choice here to make it pretty simple. 1, 0, 0. So that v there is actually the vector we call I, the unit vector that goes out in the x direction. Let's get it to print it and hit go. Okay. So you'll notice that Sage writes parentheses around vectors rather than the angle braces like we use in the book, but it's the same thing. It's just a change in notation. Let's copy this so I don't have to type so much. Paste it in here. Of course, I want to change the name of the vector, so let's make it U. I seem to always use U and V as my vectors. And what entries will it have? Well, I want this one to be the vector that we call J. So it'll have a 1 in the y coordinate and zeros elsewhere. Right? And then once you've got a vector sitting around, you can hit the dot, which will get you to the access to the member functions of the vector class, and then hit tab to see what things there are. And you'll notice way down in that list, that list is huge, but one of the things not too far down in that list is cross product. So we will take the cross product of V and U, and the question honestly is, what order does that mean? Is that V cross U or is it U cross V? And that's the reason why I picked the simple vectors that I did. If it's V cross U, then this should be I cross J, should be K. It is. Okay. So the object lesson there is if you have an expression like this, you can just read it as the math. That's V cross product with U. See how the things come in order. So yeah, now if you want to try it with something tougher, well, actually, I'll just edit these things and make a new set of vectors. How about 1, 2, 5 crossed with 0, -1, 3. I don't know what that is. Oh, wait, I just noticed I did something that I tend to do with Sage, and I caught myself this time, which is good. I made the change up here, but I didn't run the cell. So the content of the variable v is still 100. I have to hit Shift Enter in there to get it to update and revise what its estimation of the vector v is. Okay, so now I've changed the two of them, and here's their cross product. 11 minus 3 minus 1. We can verify that by hand, but I kind of trust the computer more than I trust my own hand calculations. Should I do it? I think not. Let's use this as our verification. So yeah, learn to do cross products by hand. At least at first, check your answers until you feel like there's no flaws in the way you're doing things. And then you'll be good. So check, this is just intended as a way to check your work. Okay, well that's actually going to be the end of our lecture on section 13.5. So I'll say bye, and hope you're in the midst of having a nice holiday weekend. We'll see you on Wednesday. Ciao.